break it and then see why you broke it. So we're going to make one and then break one. All right. Okay, yeah, so as he says, Krylov solvers and a little bit of GPU computing as well. Not a fantastic amount of GPU computing because they are quite orthogonal disciplines, if you will, but they do go very well together. So it's important to know that Krylov solvers really work well on GPUs, and we're going to see why that happens because of something called mixed precision coming up. So yeah, coming up, matrix inverses and their role in quantum chromodynamics. And I chose quantum chromodynamics because that's my discipline. That's what I did with Professor Geets. That's what I'm working on right now, amongst other things. But matrix inverses appear absolutely everywhere in the physical sciences and in engineering. So if you're going to have any kind of career in that direction, matrix inverses are going to be a part of your life. Then we're going to talk about Krylov solvers. And it will be a lightning review because Krylov solvers is a whole field in itself. I'm going to choose a particular Krylov solver called conjugate gradient. And we're going to take it apart and build it up and then break it, like I say, so that we have a good understanding of the quintessential Krylov solver, conjugate gradient. And then we shall go on to talk about tips and tricks, things like mixed precision on GPU, what mixed precision is, why it's useful, and how you can go wrong when you use it. Because of course it's always well and good to show somebody how good something is, but then you kind of like hide all of your mistakes. And I think it's important to actually bring some of the mistakes to light when talking about your research. And so I'll show you how not to use mixed precision and how to use it. And then lastly, just kind of for fun, we shall talk about eigenvector and multigrid methods. These are more advanced ways of using Krylov solvers. And in lattice chromodynamics, the amount of work that we ask our Krylov solvers to do necessitates the use of eigenvector and multigrid methods quite extensively. In other applications, that might be a bit of overkill. There's a nice saying in England, over-egging the pudding or gilding the lily, as it were. So people, you could use eigenvector and multigrid methods in your Krylov solvers, but then you wouldn't really see all that much speed up, right? So you're hitting the wall when it comes to speed up. So you may not need to use these ever in your life, but it'd be good to know about these methods. Okay, then. So yeah, matrix inverses and their role in quantum chromodynamics. So this is going to be a lightning review of quantum chromodynamics, another lightning review. So don't worry if none of this quite sticks long term, but I want you to understand some concepts that I'm about to give you, which is the concept of discretization and the concept of using a discrete representation of a continuous field. Because that's really what lattice quantum chromodynamics is. It is the discretization of this thing here, this Lagrangian. And this Lagrangian has this funny symbol here. It's called, this thing is called a Dirac operator. It's a differential operator. And in order to extract physics out of this Lagrangian, you have to work out its inverse. So let's just do this for a simpler example, which is quantum electrodynamics. In quantum chromodynamics, there's all sorts of problems. We don't need to talk about them. Those problems don't exist in quantum electrodynamics, and you can invert this matrix with pen and paper, happy days. And when you invert it, you expand this matrix inversion in powers of something called alpha. So what you've done is you've done some mathematics, and you realize that in order to get the actual answer that you want, you have to do what is essentially a very grown-up Taylor expansion. And the first term is, two particles or two quantum fields don't interact at all. That is the first term in your expansion. The second term in your expansion is that they interact with a single photon. And this will then turn out to be an integral that you then have to perform. You have to go to school for like 4 or 5 years and you learn your stuff. I can perform that integral. Right. That's what Feynman did. And then there are all of these higher powers, these more complicated interactions. And the integrations here are even more difficult. But luckily, every single one of these integrations has a little prefactor of what's called the fine structure constant in front of it, which is 1 over 137. So as you do the perturbation series and you get more and more complicated parts of your sum, you realize that the actual contribution is getting smaller and smaller. So you can stop at some point and say you're done. And this is great because you have to do your integration over a very wide range of energy, as you can see here on the bottom right. And this fine structure constant doesn't change very much over that range of energy. This is known as renormalization, or the running coupling of the QED coupling constant as you renormalize it. So life is good. If you just wanted to do quantum electrodynamics and you had this Lagrangian, you wouldn't need a computer at all. You would just need a good few books, a good bit of coffee or tea, whatever you like, and about 2 or 3 years to just push everything aside, learn how to do quantum field theory, and then do it. But with QCD, there's a problem. With QCD, take a look on the bottom right here. The structure constant of QCD, this alpha, the thing that was the fine structure constant, goes the other way. So as you go to higher and higher energies, that structure constant gets kind of small. That's good. But as you get to lower and lower energies, this thing gets bigger and bigger, to the point where the prefactor in front of all of these perturbation series starts to blow up and starts to get big. So now you can't even use perturbation theory, right? So you spent, 10, 15 years learning how to do perturbation theory. You want to attack quantum chromodynamics, you can't even use your favorite mathematical tool. So the only thing that we can do is to start simulating the theory numerically. And that means you have to take differential operators. These are, look at this. Don't worry about what all these things mean. What I'm trying to show you is that you can take that thing up here, this continuous differential operator, and you can discretize it. You can put it on a lattice with various different caveats and various different corners that you're cutting and things that you have to add. And what happens miraculously is that you end up simply having to solve a system of linear equations. This is something that you did in high school, right? This is high school mathematics. You've taken one of the most advanced quantum field theories that humankind knows, and with the various procedures of discretization and so on and so forth, you can reduce it down to something so simple that even a computer can solve it. Computers are the dumbest thing, they're just rocks with electricity in them. So we've done something rather miraculous here, which is expressing this very complicated theory in a very, very simple form. In QCD, this solving of this system, getting this inverse matrix, accounts for a good 90% of every single flop that we invest in quantum chromodynamics. So it's very important that we get it right. This is for two different stages. One is for the evolution of the fields, because in QCD, if you want to study how the fields evolve, you have to actually evolve them so you can see. And then every once in a while, once you have to pull out one of these fields and do some measurements on it, and even one of these requires a matrix inversion. So like I say, 80, 90%, 50, 90% at least. Well, actually, it's about 50% nowadays because our solvers are so much better. But back when I was doing all of this stuff, this was like 90%. All of it was in fast linear solvers, which is why I have become a bit of, and I say a little bit, of an expert in linear solvers, because I was presented with this problem 90% of the times in linear solvers. How do we get fast? How do we get more science? So there you go, lattice, like I say, lattice gauge theory, lightning fast. All I'm trying to do is motivate you in saying that you are going to come across problems in your career where you have a continuum. That continuum cannot be solved analytically, and you have to discretize. That will happen. Okay, we've discretized. We have a system of linear equations. So now we want to solve them. So we use a Krylov solver. What's a Krylov solver? Well, here's Mr. Krylov. Alexei Nikolaevich Krylov and his wonderful daughter Anna in 1904. He was a submarine engineer, and there are much better pictures of him out there, but I think that's just brilliant. So that's the one we're going to use. And Krylov was just a really smart guy, and he recognized that if you had a matrix A and a vector B, and you keep multiplying this vector B by the matrix A, so you can see here this span here, there is all sorts of properties between these vectors, these Krylov vectors, that you can use to identify special vectors, vectors that you want. So this B could be an eigenvector. It could be the inverse vector. It could, in other words, A inverse times B will give you another vector X, like exactly what we wanted before. And he just recognized that this particular set of vectors had some wonderful little properties. And one of the very first things that he did was known as a power iteration. So let's just see how a power iteration works. Here you can see an eigenvector equation. A matrix A times a vector nu equals an eigenvalue times that same vector nu. Well, if you know anything about linear algebra, you will know that any arbitrary vector B may be expressed as a linear combination of eigenvectors nu. And those eigenvectors are not unique, right? Any matrix A which is invertible will have an eigendecomposition And that eigen decomposition can be used to express B. Of course, the betas as well, the coefficients of all of those vectors, they're going to be different for every different eigen decomposition. But the fact remains that you can always express any vector as a sum of eigenvectors. So now what happens when you just hammer B with the matrix A? So A to the power K, so I might be doing this 100 times. This is what you're going to end up with. Beta I, that doesn't change. And then lambda K will come in, multiplied by the eigenvector I. So I'm just going to offer this up now very quickly. Is anybody brave enough to know what this particular right-hand side is going to look like after, say, 1,000 matrix iterations? What do you think this right-hand side is going to be?
Like if lambda is really small, then it will go to 0. If lambda is like greater than 1, it will grow like really big, I expect.
That's the one. That's exactly right. All of the small eigenvalues will be sent to 0 because they're smaller than 1. All of the very large eigenvalues are going to be multiplied. So if this is, say, if lambda here is 10, and I raise it to the power of 1,000, it's going to dominate all of the other eigenvalues. So what happens is the largest eigenvalue starts to shine through, and the smallest eigenvalues start to get suppressed. This is the very nature of a power iteration. And you can see that's what's happening inside this Krylov space. Inside the Krylov space, you have this power iteration happening. So a suppression and enhancement of particular eigenvalues is the mechanism through which Krylov solvers are working. That's the general idea. But that's how they do it. So let's see. Let's see. What's next? The conjugate gradient algorithm. Here it is on the left. The conjugate gradient algorithm. We can use this Krylov space to build up a series of vectors. And because we know exactly what we want, for example, in the conjugate gradient algorithm, we know we want the inverse, we can kind of manipulate each one of the Krylov subspace vectors as we build it so that we, just very slightly rotate them in the direction that we want. I.e., I want to find what happens when the matrix A inverse is applied to a vector B. That's what I want to solve. And this is the algorithm that will do it. And you can study this and you can look at it. But I just want to give you general ideas here and then actually get hands-on with some code rather than having a very dry, terse, lesson about algorithms, because there's billions of different ways in which you can learn about this. But what I want to show you is that the conjugate gradient inverter algorithm essentially maps a matrix B to a matrix X using only A times B operations. Here is the A times B operation here. See that? A times P? That's where you do the matrix vector operation. And then you do a variety of linear algebra computations. These alphas and these betas are essentially measurements of how bad you're doing or how good you're doing. And then every single step in the solver, you are rotating this P vector in the direction that you want. I want you to think about this for a second. A matrix does two things to a vector. Number one, it can scale the vector, so it can make the vector larger or smaller. And number two, it can rotate a vector. That's all a matrix does. A matrix both rotates and scales a vector. So what we're doing here is by repeatedly applying the matrix A to this vector P, is we're measuring, hey, did that bring us any closer to the inverse or any further away? And these inner products, these measurements here, measure how good you are. You see here, let's just actually read this first line. R naught equals B minus A times X naught, where X naught is your initial guess. Let's say that you nailed it. Let's say that you got exactly what you wanted, that X is actually equal to A inverse times B. We'll take a look at that. A times A inverse times B gives you B minus B, and R naught is 0. So R naught is a measure of how good you're doing. If R naught were the 0 vector, then your X vector, the one that you want, would be perfect. But invariably, it's not right. It's not quite right, and you have to incrementally rotate this X vector to get to where you want. And that's how CG works. You have to read it, and you have to look at it, and you have to understand it to really get a feel for these algorithms, how they work. Rest assured, a lot of people don't even bother. They just understand that CG is an algorithm that does something that they want, and they never think about it again. But it pays to think about the black boxes that you use in your sciences. So okay, there's your conjugate gradient. Like I say, we can stare at it, we can look at it, we can talk about it. I'd rather not. Let's just actually have a demo. Let's run some conjugate gradient. So here I have some code for us all to git clone. Let me think. How can I know how to do this. Let me escape.
I was going to say, Dean, I actually, in part of the boot camp series that I did this time, I actually showed them how to clone Git repositories. So,
oh, beautiful. Absolutely superb. So well, I'm going to...
Hopefully they won't have an issue with that.
Good. Actually, let me find it. This is still uploading. That's terrible. I'm going to find... there you go. That'll do. I'm going to find the command because I can't actually... slides. So I'm going to put that in the Slack when I find a way to... How do I find a way to chat? There's no way to chat. There must be. I have to stop staring at my machine. There we go. There's the chat. So there's your git clone. There's your git clone. So if you take that and you put it in the command line, it will pull some code down for you. And there it is. And I'm going to do this with you. So if you get super left behind, just let me know and we'll play catch up. Because this is a kind of an important part of this lecture. I didn't want to give you an hour and a half of lecture. That just seems like a nightmare to me. Even I don't want to do that, and I'm the lecturer, right? Who wants to actually listen to somebody talk for an hour and a half? So we're just going to talk for a bit, play around with some code, look at the code, look at the algorithm in the code, see how they interplay with each other, and then we're just going to push through as much information as we can through the end. But I want you to get to this point where you have seen conjugate gradient, you've seen the inner workings, you've seen the code, so it's not a black box for you anymore. This is literally lines of code with every single flop accounted for. It's not just a function that you have to trust. You can actually see it. Okay, so I'm going to do this with you. Good. So I want that. I want a brand new screen. Okay, make deal. Temp RPI demo. So I git clone, and down comes all of this stuff, RPI Advanced Cyber Infrastructure, blah, 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 blah. What did I ask you to do? I asked you to change directory into RPI Advanced Infrastructure 2020. Oh, there's a lot of stuff in there, by the way. There's a lecture I gave last year. All the stuff is in there, so if you get super curious, you can have a look around. In 2020. And what do we have? We have a cg.c, so we're going to compile it. So you've had a boot camp, so you've seen this before. Let's see. There you go. G++, cg.c, and then the output is just cg. You can change that whatever you want. That's just what the executable is going to look like. So G++, cg.c -lcg. Let's do that. And it compiles. So it compiles, and if you have a look in that directory, there is an executable, which I've called CG. You might call it something different. Does anybody not have that executable in their command line right now? Let's take stock. If everybody has it, then we're going to move along. Yeah, life is good. Speak now or forever hold your peace. Okay, well I'm gonna
have that executable.
Go ahead.
I do not have that executable yet.
Okay.
Whereabouts
are you? Did you download it?
Yes, I did the git clone, and I created the directory and then did the git clone. But when I run the G++ line, I get an error that says no such file or directory.
Okay, so press pwd, type pwd, and what does it say?
It says I'm in the directory that I just made. I just called it demo.
Right, so you need to change into RPI Advanced Cyber Infrastructure 2022. So you need to change directory into those two directories. So CD RPI Advanced Infrastructure 2022. And then when you do that, now rerun the compiler invocation, G++, blah, 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 blah.
See, I'm in that RPI Advanced Cyber Infrastructure, and my compilation gives me the same error of no such file or directory.
Did you go into the 2022 subdirectory?
That I did.
When you've been doing it this long, you just know where all the bugs are, and because I've done all this myself. Trust me, I've made every single one of these mistakes you're making, so I've been there before. So if you're inside that 2022 subdirectory, and then you give me the compiler indication invocation, then you should get an executable. All good? All good? Cool. Right. So let's just be cavalier, and let's just run it. Oh, error in command line parameters. N, maxiter, tolt, diagonal. So my code is giving you a hint. If you run it and you give it no arguments, it tells you you're not giving it the right command line arguments. And the command line arguments are N, it's going to be the size of the matrix N, the maximum iterations of the conjugate gradient solver, the tolerance to which you want the conjugate gradient solver, and something special called a diagonal, right? So that's it. Okay, so let's just pretend we're Alice in Wonderland here, right? Like, what's going on? So I don't know. You want to know what's going on here. You've just been given an error message. So let's actually have a look at the code, cg.c. And as always, we go to main. So we're looking at main. So yeah, sure. All of those little things that I told you about are getting pulled in. The maximum iterations, the tolerance, the diagonal, 150. And you need to set them. So let's just find out what is the tolerance. Tolerance seems to be a very small number. These are the defaults. The tolerance is a very small number. That tolerance is the L2 norm, the Frobenius norm, the Pythagorean norm, if you will, of that thing we called the residual, that R vector. So R, remember, was a measurement of how good our X vector was. We were applying the matrix vector to X repeatedly to try and map it from where it was to where we wanted it to be. And R was a measure of how good the X was. So if R is if the residual norm or the L2 norm of that R vector is extremely small, what it means is we've done a pretty good job. Let's just remind ourselves, again, I'm sharing my screen. I swear that thing just all the time closes itself for no reason. It is the most buggy. There it is. It's the most buggy. Here we go. So the tolerance is a measurement of this R here. If RK+1 is sufficiently small, then exit the loop. So if the size of this residual vector is sufficiently small, then we're done. That's what the tolerance is giving us. Okay, jolly good. The diagonal. Okay, the diagonal is just something that we add to the problem matrix. So I make a problem matrix, so you can see what's going on here now. We've got a bit of a bit of fancy stuff, a little bit of starting and creating some memory. Then I create a boatload of random numbers. There you go. And then I populate a matrix with those random numbers. But look at how I'm doing it. I'm taking a random number and I'm adding its opposite, as it were. So I'm taking a random number in ik, and then I'm adding ki to it. And then along the matrix diagonal, I'm adding a really large number. What is that doing? That's actually, it's kind of cheating for me, because conjugate gradient only works with orthogonal matrices. And if it were a complex matrix, it would be a Metian matrix. But even that isn't good enough. For conjugate gradient to work, every single one of those eigenvalues has to be positive. If you get a negative eigenvalue in conjugate gradient, it starts to flip around. And when it starts to flip around like that, because of course you're just applying the matrix to it all the time, so it goes positive, negative, positive, negative. When it starts to flip around, conjugate gradient gets completely lost. And I'll show you that that's what happens in conjugate gradient. We don't have to wait for a particular problem. I can show you. Now you've got a little bit of a treat now. Now you've got some OpenACC. So you have actually got some GPU computing going on here, and you can use multi-core computing as well. So OpenACC will do all of this stuff on a GPU for you. And the last time I gave this lecture, I had like 2 lecture spots, so I did a lot of stuff on OpenACC. This time around, I'm not, but luckily for you, I wrote everything that you need to know inside this file. All of those pragmas and all those OpenACC directives are all explained in reasonable detail so that you won't get lost if you take the time to just read through what this code does. And what is it? It's 296 lines of code. This is not a lot of code. So if you just read through this, not only will you understand what conjugate gradient does and how it works, you will also get to learn about how OpenACC can be used in all of these functions to accelerate your code. And if that's too much for you, there's another one, which I included, called Simple. Simple.c. Simple.c is compiled in exactly the same way as CG is. And all it has is a vector multiplication and a vector addition and a vector fill. And it shows you how you would create vectors and then manipulate those vectors on the GPU, and then there's your time. So you can see how this will work. So you need to go in, you need to just read through this when you have a moment and nobody's around, and you can just see what's going on, because taking in what code does, what you see on the screen, what it does in your head and what it does in the computer is a little map that you have to build for yourself. There's a lot of abstract stuff going on here, and I don't want to pollute your minds with my abstract thoughts about what all of this stuff is really doing. You need to actually go away and just think, okay, so this guy's told me that this algorithm does this. Okay, fine. He's told me that this code does that. That's fine. You need to work out how those two are working, how those two are bridging the gap. And I've given you the very simplest possible algorithm to do that. But anyway, back to CG. Back to CG. So what we've seen is that we've created a matrix. That matrix has been made positive definite or positive semi-definite, which means all of its eigenvalues are positive. And then we just run conjugate gradient. Let's actually just look at conjugate gradient. Why not? Like I say, you have to read this code, look at the algorithm, look at the code in your own time, match the two things up, see what's what. But you'll see that it will iterate until it converges. And after it's converged, we always do a check. This check is here. So X is our candidate solution. And we multiply our candidate solution by the matrix. So what we're left with here, or what we're actually doing, is A times A inverse on B, which is equal to A times X, which should equal B. As if we look, A times A inverse times B, which is equal to A times your candidate solution, should give you back your original source. And that's what we check for here. We multiply this candidate solution times A by -1 and add it to B, and we should get, and then we get a residual, and we should get 0 here. So this true residual squared, that should be a really small number when we're done. Well, let's check it, right? We've seen enough. You can do this too. Don't just watch me. I want you to do it too. So we'll make sure we've compiled. Yep, it's compiled. Good. We try and run it again, but of course we forget because, you know, we're human beings. Oh yeah, that's right. We have to put in numbers. This is how you put in numbers. I'm going to put in 1024 because we all like binary numbers. Max iter, let's just call it 1000. Why not? For a tolerance, I'm going to be quite strict. I want 1e to the -12. So the size of this vector, this is a vector of 1024 real numbers. When I square and add up all of the 1024 real numbers from the residual, the sum has to be less than 1e to the -12. So that's a pretty small number. That's pretty small. All of this vector has to be pretty close to the 0 vector. And my diagonal, I'm going to make 80, whatever. No, I'm not. I'm going to make it 30. There you go. That means that all of my eigenvalues of the original matrix, whether they were positive or negative, will all be shifted by 30. That's how that works. That's what happens when you add a diagonal to a matrix. All of the eigenvalues get shifted to the right. Let's run it. Boom, done. Look at that. That was fast. Nicely done. And you see CG will report to you that after iteration 1, that thing that I use to measure how good my guess is, the residual, that is that big. And it gets slowly smaller and smaller and smaller, which tells me that my algorithm is working. This is why it's very important to eyeball the output from your algorithms when you do this. Your algorithm is working. It's doing what I expected it to do. The residual, this measurement of how good my candidate inverse is getting smaller and smaller and smaller as the algorithm progresses. Until eventually, the size of that residual is less than the tolerance that I requested, which is 1e to the minus 12. That's when the algorithm stops. It does its check and says, yeah, your candidate has a residual squared of that. When I actually check it, it's that. That actually works. Life is good. And then, okay, so there's some extra stuff here. I now run conjugate gradient with an initial guess. But let's just forget that bit for a second. Let's just run this again. But now, let's make these eigenvalues a little bit smaller. Let's make them 26. So I'm just going to shift them not by 30, but by 26. So that means my smallest eigenvalue just got 4 smaller. Let's see what happens. It took the original algorithm 55 iterations to get to a solution. Now I've reduced the eigenvalues by not a factor of 4, by an amount of 4. Let's see what happens to CG. Ooh. Took a bit longer. Took 138 iterations now. So now CG is getting stressed out a bit. It's like, whoa, what's going on? These eigenvalues that I'm trying to get rid of are even bigger. And the eigenvalues that I want, they're even smaller. So it has to work really, really hard to find all of these numbers that it wants. But it managed to converge. You know, no stress. It took a little bit longer and it converged. All right. So let's break it. Let's break CG. Let's see what happens when we go 25. Just do it one at a time now. Ooh. Get a bit wobbly. Now it's taken 254. Okay, let's just break it. Oh dear. Oh dear, oh dear, oh dear. Well, it was kind of getting there. 1,000 iterations. It was kind of getting there. But we put maximum iterations of 1,000, so that actually failed. Let's see if we can make it work. Let's see if we can give it 10,000 iterations and it'll finally get there. Yeah, it does. It finally gets there. All right, let's really break it. Let's just have 0. Nope, now we're just wasting our life. We're just wasting time. We're wasting computer time. Oh, are we? Ah, so CG can surprise you. Yeah, it can finally get there. So even though, you know, even though these eigenvalues that it's trying to get rid of and trying to suppress are really kind of small and they're flipping around, conjugate gradient actually can get you to where you want to be. So even though these negative eigenvalues flipping around are polluting the search space, CG will just keep grinding and keep going and keep doing what you ask it to do until it gets you a solution. So it's pretty awesome. That's why we like CG, because it generally always tends to get you the right answer, even if you have to wait for a very long time, which in lattice gauge theory absolutely happens. However, let's take a look inside CG and see what we have in store for this algorithm, because this algorithm has just really impressed us. Now we're going to break it. Here I have a define float, and it used to be double. That means everything was going on in double precision. We're going to change that. We're going to change that to float. So now everything is going on in single precision. If you don't know what double and single are, don't worry, we'll go through that later on. Really what I'm saying is that float has less information. There is less information inside a float number than there is in a double number. So now nothing is really quite as accurate. So compile it. And we saw that this one took about 3,000 iterations, but it got there in double precision. Let's see what happens in single precision. Absolutely not, CG says. Absolutely not. You've got no chance. Look at those numbers. Let's just stop and look at those numbers. Right, we're at 3,000 now. Look at that. What, 10, 21, 15? This is no good. I asked for 10 to the power minus 12. This thing is never in a million years getting me where I want to be. Never. And we could wait around forever. So single precision seems to be poisonous to a conjugate gradient solver. And so if you were to develop a conjugate gradient solver, say in, I don't know, 1987, because QCD had just been discretized and everybody was rushing to try and get some information out of this, you say, let's do it all in single because single's faster. They go, oh, you know, we tried it, but it didn't work. We have to do it in double. So everything was done in double precision, absolutely everything, because nothing works in single precision. And that's where we are. That's where we were, sorry. But anyway, we're going to progress from that. We're going to learn about how we deal with things like this single precision and this double precision. But here you go. There's your CG algorithm. Play with it. Have fun with it. Explore it. Get used to how it behaves, because you will be using a Krylov solver sometime in your research if you're going to do numerical stuff. There will be a Krylov type solver in there. Sometimes it will fail. Sometimes it will work. And you don't want to be the person that says, I don't really know why it's doing that. You don't want to be the person that says, I don't know why my Krylov solver is or isn't working. You want to say, oh, the reason our Krylov solver is not working is because of this parameter and this parameter, and we must change this. And that's how you can get around it. That's how you can understand what your Krylov solver is doing. And you will see Krylov solvers behaving like this, you know, where the residual norm just gets worse and worse and worse. What's happening is all of the junk information from single precision is just building up and building up and building up until eventually it's actually moving you way, way further away from where you want to go. You can, there's actually a really delicate spot that I found. Let me see. No, not simple commands. It was the prep problem. There it is. Yeah, there it is. So I'm going to run that in 25. Yeah, there we go. We run that in 25 in single precision. And it fails to converge. It just fails to converge in single precision. I wonder if it will just keep going though. Let's see. Would it just keep going in single precision? It would work, yeah. That's nice. Let's try 24. There's a point where this algorithm will just grind to a halt, and this happens an awful lot in sciences. Oh well, maybe not today. Well, there's a delicate point. There's a delicate point where this number, this diagonal, is so close to the smallest eigenvalue that you basically have a zero eigenvalue, and this the size of the eigenvalue is so small that single precision can't even represent it, and so it will just get stuck here. That's another thing that CG will do, is it will get stuck at a particular residual, and the reason for that is because of the condition of the matrix. But anyway, there you go. There's your CG. Let's just have a quick look at it over again. There's your CG, which you can play with and learn about some ACC with. You have a very basic setup. It makes the matrix that you want out of rands. It solves it. It does this thing called an initial guess, which you should play around with and have a look at. Let's actually just, what time is it? Yeah, what time? Let me just explain what an initial guess does. Let's see, because this is actually quite useful. So if you were to pass the zero vector as your initial guess, so you have no idea, you have absolutely no idea what a good initial guess would be, that's fine. You can pass in any vector that you want, and that vector would represent an initial guess. Sometimes people literally just put in 0 as the initial guess, and let's see what happens. If you put in 0 as the initial guess, you actually just use your source as an initial guess. So this B vector, this source vector, in terms of physics, let me explain this. This might represent a quantum mechanical field at time 0. So you have a nice quantum mechanical field defined over a space-time at time t equals 0. Your Krylov solver computes A inverse times that quantum mechanical field. In other words, what it would compute for you is how that quantum mechanical field will evolve with time. That's what your matrix can do. And of course, we want to know this. We want to know how this B field evolves with time. That evolution with time is locked up in our differential operator, whatever it might be, in QCD or in fluid dynamics or Navier-Stokes, whatever it is. And our solution X is what happens to our initial quantum mechanical field after all of the evolution is done. And if we have no idea what the best guess would be, we just use the original source as a guess. Why not? You know, any guess will do. But you can, if you wanted to, supply it with an original guess. And when you do that, let's see what happens. We have to fix this. We have to fix this. Let's fix that to 30. That's fine. No, let's make it really good so it's all fits on the same page. There you go. So now you see, just have a look. I put 50 as my diagonal. So now all of my eigenvalues are really kind of chunky. So CG has a really easy time finding everything. Then what I did is I took the solution from the original problem and I used that as a guess in the next problem. And you can see the first problem took 29 iterations to be solved and the second one took 16. So using the initial guess really worked. And that initial guess, this is kind of a bit of fudge. I'll show you. It's a complete fudge. All I did was change the matrix very slightly. I just added a tiny, tiny little number to the diagonal of the matrix. So it's almost the same matrix, but not quite the same matrix. So the guess from the last matrix that I used is the solution, not the guess, the solution from the last problem that I solved is an extremely good guess for the next problem. The next problem is the same matrix with a tiny, tiny, tiny perturbation down the middle. And the previous solution was a superb guess for the next problem. And you can see it. Look at that. It starts almost done. The first one, that measurement of how good we're doing, it's like order 1. And you have to wait all this time to get to where you want to be. The second time, I actually use a good guess. Look at that. I'm practically already there. So that second guess starts us off in the map pretty halfway through. This is a very useful property of CG, as we'll see in a bit. But here, let me just warn you that this isn't always going to work. What happens if I, say, did nothing with the matrix? So now this is exactly the same matrix as before. But I take my answer and I take off a tiny, tiny, tiny amount from just the 0th element. So this is exactly the same solution vector as before with a tiny, tiny, and I mean tiny, modification to one of the elements. That's all I'm going to do. Make it. Here we go. Plus, let's make it, yeah. That's fine. Don't worry about it. Oh, I did it wrong. Equals minus. That's no good. Minus equals. Got that the wrong way around. Let's run it. Okay, that was a bit too small then. That was a bit too small. Let's make it a bit more on order. 1e to the minus 4. So there you go. So there's the original problem, exactly the same as before, solves in 29 steps. And then instead of changing the matrix slightly, I changed one element of the solution vector out of 1024. And I changed it by the same amount that I changed the entire matrix. And yeah, sure, you might argue that that's okay, but that's pretty bad, right? I mean, you would think that that original guess from the last solution would be almost perfect. Like it simply has one element to do. But no, you actually kind of shoot yourself in the foot. So this is the kind of stuff that you can do with a conjugate gradient solver written in C. You can play around very easily with all of these types of things that you can do with the algorithm and just study it and observe it and see how it works and play around with it. But there you go. We're done with CG for the moment. So let's move over to my closed. There we go. My closed keynote because it's disappeared again. Don't know why it does that. And now we're going to power on through for the rest of this presentation. There'll be a little bit of a code demonstration later on, but not as hands-on as that. So yeah, there's your algorithm. Let's just quickly go over what happens again. You have a matrix A. You wish to compute A inverse times B. And with repeated application of the matrix A, you can slowly map your initial guess X to where you want it to be. And there's 1,000,001 different variations of conjugate gradient. There's biconjugate gradient stabilized, there's greatest conjugate residual, there's the ICG. There are all sorts of algorithms out there which are better at solving some problems than others, but they're all variations on conjugate gradient. If you get a good handle on how conjugate gradient works in your own way, in your own abstract mind, you'll have a much easier time understanding how other algorithms work. If you just decide that conjugate gradient is just not something you're interested in, and you'd rather it just be a little black box in your code, then what will happen is that black box in your code will become more and more important and more prevalent, to the point where somebody will say to you, if you want to make progress in your scientific field, you have to make that Krylov solver 10 times faster, at which point you'll say, I wish I paid attention to Krylov solvers when I was a student. Because otherwise, you're just letting somebody or something else dictate how your science gets done. So, because that's where we're at. That's where we're at in science right now. There's, like I say, there is the algorithm. There is how you pull down all the code. And there is the algorithm just written out, right? So you have to make that map. I want you to make that map. Read that, pull that down, have a look through that, read through that, and make the associations in however you like. And then just, they don't have to be concrete. You don't have to be writing papers on conjugate gradient because you found something right. Just understand what all these steps do. So some key points. Key points. The convergence of a Krylov solver depends on the condition number of the matrix. That is the ratio of the largest eigenvalue to the smallest eigenvalue. If the condition number is large, it's going to take you a long time to converge. That's just a given. In quantum chromodynamics, these condition numbers can be 10 to the power 9. That's pretty bad for a conjugate gradient. So we need a lot of tips and tricks to make this work. But as you've seen, if you add a diagonal to your problem matrix, you can solve it a lot faster, because the condition number of this on the right is a lot less than the condition number on the left. And you can actually use that trick if you want to solve some matrices, especially if you want to do eigen decompositions. Because if you just add constants to eigenvalues and you identify eigenvalues, you can always just take that constant away. So you can do all sorts of wonderful tricks with eigensolvers using this here. Just a quick note, the conjugate gradient only works for positive definite matrices. That's if you have, I say it only works, it works best for positive definite matrices. If you have some negative eigenvalues, like I say, they can really play around with how the search space works. If you get it really bad, then it won't converge at all. But conjugate gradient is quite robust. But in general, people say it only works for positive definite matrices. Negative eigenvalues, yeah, they can pull it the search direction. And yeah, you can't just cheat and do everything in single precision. Because if you do some things in single precision, you get round-off error. You get a lot of error that builds up in your algorithm, and you have to revert to double. And this was a lesson that people learned a while ago. They just said, look, we can't use single precision, we have to use double precision. And they used double precision for a long time because they all got burned by this problem of trying to use single precision. And it wasn't until somebody came along and actually knew what they were doing. Wait, I got a question here. Yeah, it wasn't until they knew what they were doing that single precision was brought back in. Okay, so Taylor Powell asks, so then is there a practical limit to the reasonable range for plus C? Is it just a matter for the limits of double precision? I mean, if you added, yeah, like if you added like a gigantic number like 10 to the power 12, then you kind of ruin the information in the eigenvalues, right? So an eigenvalue might be something like 10 to the power minus 6, and then there's a boatload of information contained in the double. And if you add 10 to the power 12 to 10 to the power minus 6, there's a huge gap between all of the information from the very large number and all of the information from the very small number. So you actually lose data, because the very large number just starts to dominate. If you actually look, I'll show you now, actually. That's a really good question. And I'll show you, I think, in the, in mixed precision, low precision representation. That really dovetails very nicely. Here is what we are looking at when we look at double precision representations and single precision representations. Here is your double precision representation, and here is your single precision representation. And all of the information, the actual numbers, are here. And then this bit is the scale. So this is like the 10 to the power part. So you've got some information here that you have to preserve, information here that you have to preserve, and then there's some information also here which tells you where that information lies on the number line. And if this number here is 10 to the power 12, and then you have another double number which is 10 to the power minus 6, then all of the very large number information dominates over the smaller one. It's like if I tell you I can represent a decimal number to 5 decimal places, you go, okay, cool, that's really cool. Yeah, okay, cool. And then I say, okay, add the number 1 times 10 to the power minus 5 to 1 times 10 to the power 5. And I'm like, well, wait a minute. Those bits of information, they're like 10 decimal places apart. Like the 1 times 10 to the 5 is 5 decimal places to the left, and 10 to the power minus 5, that's 5 decimal places to the right. And I can only represent 5 decimal places. So I've just lost the small information. That's exactly what happens. There are only a finite number of decimals that a number, a binary number, can represent accurately. Once you get further and further down the decimal scale, these binary representations get worse and worse and worse. And this is a real problem. This is a real practical problem when it comes to doing number crunching on computers, and we have to be very cognizant of it. So this is why, by the way, this one is called double and this one is called float, because everybody started with float. Nobody started with double. That makes no sense. Why would you start with double? You start with float. Everybody thought that float was good enough. 32 binary numbers, 32 binary digits, broken up so you have a sign, so you have an exponent for the scale, and a mantissa to represent the number. Everybody thought that was fine until they got really serious about computing, and they were like, man, our CG solvers just are grinding to a halt. They're not actually working. And they bit the bullet and they said, let's actually do things in double precision. So now in double precision, you can represent more decimal places and you get more accurate answers. Life is good. But, you know, that doesn't mean to say that smaller data representations are bad. Here is double, here is single or float. This one's half. So this is now, you know, even fewer decimal places, even fewer decimal places are able to be represented. But you can still do you can still do good stuff with it. People still actually do use half precision. Indeed, Google used half precision for a long time in their machine learning applications. But what they found is that half precision can't represent the same range of numbers as single precision. Look here. In the exponent, you have all of these bits that represent the range of a number. So this is the 10 to the power part. You move to half precision, and you can't represent anywhere near the same range as single precision. And they were having real problems, like, what's going on? What's the problem? What's the problem? So they just came up with their own standard. They just said, you know what? We have 16 binary digits. Let's use the same number of exponent bits in our representation, known as B-float, as we do in single precision. So now you can represent the same range of numbers with B-float 16 as you can with single precision. You just don't quite have the same accuracy. But that's fine, Google said. We need to be able to represent all of these ranges of numbers. The actual accuracy isn't all that important. So what's the lesson? The lesson here is that using smaller representations of data can be a bit of a poison pill. It can ruin your life and it can just make things terrible. Or you can see it as using the right tool for the right job. Google didn't need all of this single precision information. They didn't need all of those bits at the end. When they used half precision, they didn't need all of these bits either. So they came up with a compromise. They used the right tool for the right job. That is the lesson to learn when it comes to mixed precision. The data that you need to represent need only be represented by the data representation that suits that data. You don't need to know, like if you heard the old chestnut, if you knew pi to 16 decimal places, you could measure the universe to the width of a hydrogen atom. So why write down pi to anything more than 16 decimal places? That's what a computer scientist would tell you. Of course, a mathematician would be like, oh, there's all sorts of beautiful things. But a computer scientist says, if you know pi to 20 decimal places, you're done. Because that's all the numbers care about. So let's see how we use different precisions in conjugate gradient. And we kind of have an understanding of how it breaks now. So this is a much easier conversation I can have with you. What happens in conjugate gradient when you use low precision stuff is it breaks down. You get all of these eigenvalues that are fluctuating and the single precision can't handle them, can't suppress them properly. If you want to use mixed precision in CG, you have to replace all of these operations with single precision, but somehow account for all of those errors that are happening and building up. You have to see all of those errors turning up and squash them when they turn around. So this is how it's done. This is your mixed precision solver. So there's two different precisions going on now. There's a target precision, which is kind of red, and there is a low precision, which I've kind of done in blue. And there are some rules that may never, ever, ever be broken when it comes to mixed precision solvers, or they will fail. That is, you always do reductions in target precision. So we want our target precision is double. We want our answers in double. And a reduction is when you add up a boatload of numbers. Say, for example, if you were to measure the residual norm of a vector. You have 10,000 numbers, you square them all, and then you add them all up. If you're going to add them all up, you better add them all up in double precision. You can multiply them in single precision when you square them, that's fine. But when you add them up, you must add them up in double precision. That way you don't accumulate a boatload of terrible errors. There is a neater form of the inner form here. This is called the Pollack-Ribier measurement of the inner form. See here, this inner norm is the current residual divided by the previous residual. That's what this beta is. It's the current residual, k plus 1, divided by the previous residual. The Pollack-Ribier form kind of mixes it all up and looks not only at the ratio of the residua, but the actual difference of the two residua. So there's a bit more information in there. So this is just more like a grown-up version of the beta k. Here, this step here, this is a very important step. This is known as the correction step. This is the part that resets the solver. So normally what would be happening is that you would look at the residual norm, and when it gets small enough, you stop. And sometimes it doesn't get small enough, so it goes on forever. We break this step up. So this is a very binary step. Look, is it small enough or is it not? If it's small enough, stop. If it isn't small enough, keep going. Here you see that we actually measure, every single iteration, we measure the size of the residual norm. Is it less than this delta times the size of b? Delta is a tunable parameter. It's called the reliable delta. And when this residual norm gets smaller than that, then we have to pull in what's called a correction step. So we do a step of the conjugate gradient algorithm with a full double precision operator. So you could run this in single precision, and as you saw, the single precision algorithm will work for a little bit, and then it will start to go a bit haywire. This measures the haywireness, as it were, of this algorithm. It says, oh, life is getting pretty bad right now. Something's going on. And you use what you have as an initial guess in double precision, and then just continue in single precision. So you saw earlier in the code demonstration that you could use an initial guess in conjugate gradient to kind of like jump down the queue, down the line, to see where you were, to get a head start. You take advantage of this when you use mixed precision. So what you do is you run conjugate gradient in single precision or half precision or whatever in a low precision until you sense that your algorithm is starting to break down. At that point, you stop. You do a singular double precision matrix vector operation that kind of like corrects all of the errors that you've done, because everything is now done in target precision, and your Krylov solver is back on track, and you can continue running in single precision. And you only really need to typically do something like 1% of your iterations need to be done in double, and the rest of them can be done in single. And that's how you use mixed precision. And look at how subtle the changes are. Sitting around in conjugate gradient for nearly a decade was this, and nobody used it. And the reason nobody used it is because even doing single precision isn't all that much faster than double precision on a CPU. And then in about 2008, boom, the GPUs came along. And the GPUs, they can perform single precision and half precision stuff way faster than they can in double. In fact, it's about a factor of 2. So single precision really does go twice as fast as double precision, and half precision really does go twice as fast as single precision. So here are just some plots of how conjugate gradient solvers behave with various mixed precision in there. Here we have the black line, which is double half. So the target precision is double, and the low precision was done in half. And it was done in the naive way, where none of these Pollack-Ribier things were happening, and none of these correction steps were done. And you can see it just goes haywire. It just goes wrong. We saw that. We saw that happening when we had a really, really bad matrix. Here is the This is the condition. This is a really, really bad matrix because the mass is kind of small. So you see the condition number is huge. So the black line shows the conjugate gradient solver just having a really bad time, and it's never going to converge. Then we see the green one. This is the green one. This is just running everything in double. It's running everything in double. This is the target. And then we have double half with all of the fancy bits, and they're not even that fancy, put into conjugate gradient. And you can see that it really does behave very well. The number of iterations is slightly bigger, but don't worry about that because GPUs can do this red line way faster than they can do the green line. Now just look at the red line as well. You see these spikes. Look at those spikes in the true residual. Would somebody care to guess what these spikes are? What's going on with these spikes? Why is the residual, in other words, my guess of my measurement of how good my guess is, why is it suddenly spiking? What's going on? Well, I'll tell you because we've got a bit of time. You see here on the black line, it starts to spike. Those are just the errors that are building up in your low precision solver. If you don't take care of all of the errors in your low precision solver, then your Krylov solver will just have these violent changes in the direction of the vector because it's got all of this junk information. So it's like being slammed by a car. You know, you just keep driving off in the wrong direction. So what's happening here on the red line is that it's moving along nicely. Life is good, life is great, life is good, life is great. And then, I've just detected a shift, right? This is exactly the point in your algorithm where it says like, hey, using this low precision, it's not working for me. So you trigger a double precision correction step. And that's why all of these deviations never get more than one single line. You measure a deviation and you go, we just went wrong. So the solver stops, does a double precision matrix vector operation to restart the solver, and then you rock and roll. And this solver restarted once, twice, 3 times, 4 times, 5 times, 6 times, and then it was done. So there were 6 double precision matrix vector operations out of about 40,000. The rest of them were all single. Oh, sorry, the rest of them were all half. And look at how well they behave. Look at how well they behave. So you can do it. You can use mixed precision in your solvers. Okay, there's a question there. Let me just look at this question. Has there been any research or information regarding the sweet spot between the precision and the C quantity, like adding a bigger C and using something like a long double? That's a superb question. Long double or quad precision, as it were, is on the horizon. It's going to happen. It's going to happen definitely in lattice gauge theory because we're now dealing with problems that are so big that we are encountering the same problems with double precision representations as we did back in the day with single. We're starting to see errors creeping in. We're starting to see things going down the wrong road and breaking down with double precision. Our problems are so large that we need double precision stuff. So researching things like double precision, long double precision, or even something like 80-bit, which is somewhere in between 64-bit and 128. People are also researching that because remember, if you're going to build a 128-bit float machine, it better be able to do 128 bits, and this is like so you have to re-engineer all this stuff. The IEEE standard is for 64-bit. That's double. If you're going to be a mathematician or a computer scientist and say, hey, guys, we need 128 bits to do our science, somebody has to go away and design that machine. Maybe they don't want to do 128 bits. Maybe they want to do something like an FPGA, a field programmable gate array that allows you to decide how many bits you want, what you want your data to be. So there's some shifts going on in computer science right now in architecture design. You know, it's not just a case of buy the computer and run the code. The computer scientists are saying, here are the problems that we're running into trying to do science. And so the architecture designers are saying, right, how do we best design a chip or a computer that can best serve numerical people? These are the kind of problems that are being exchanged. Is memory not going to be an issue when you've doubled the amount of space? Yeah, always. Memory is always an issue. Totally. Absolutely. Always going to be an issue. Memory will always be an issue. Full stop. Like, we only have a finite amount of memory on a machine, and if you've used it all, you need more machine. And if there's no more machine, you have to go to the government, ask for another machine. It's non-stop. Okay. All right, so let's see what happens. Okay, here's just some pretty plots. Sorry, this is me just showing off because this is some data. This is what happens when you use double precision, double single, double half. You know, obviously it gets faster. That was in something called the Milk CG solver. This was some of my work that I did with an NC equals 4 theory. This is a 4-color theory. This is like a very weird version of QCD where there are 4 colors but not 3 colors, which has some uses in dark matter stuff. But again, we see improvements. So all I'm saying here is like, yeah, it works, it improves. But let's do a CUDA demo, right? I want to show you this working. Now, I'm not going to show you the code this time because that would be a nightmare, because CUDA was a nightmare for me for a long time until I learned to love it and program in CUDA. And I do all of my QCD codes in this CUDA code. We're not going to see it, but we are going to use it. All right. So let me just introduce you to this problem very quickly. Sorry, was somebody going to ask a question? No, there's no questions. All right, okay, fine.
I accidentally unmuted my mic. That was it.
Okay. Oh, okay, right, good. So here is this is just a command line invocation, right? So this is just sending information to a conjugate gradient solver. Nothing fancy is going on here. It looks a bit different. I'll take you through what's going on. The DIMs are 16, 16, 16, and 64. So for this problem, the matrix size is 16 times 16 times 16 times 64. It's a big matrix. And not only that, there are 12 numbers at every site of the matrix, 12 complex numbers. It's a very, very beefy matrix. It's a big matrix. The target precision, prec, is going to be in double. Verbose just means tell me what's going on. Mass is kind of like this diagonal. Now, you can't play with the mass like you can before, right, and get right numbers, because the mass represents the mass of the underlying particles. That's kind of fixed, but it's very much like the diagonal that we saw before. Anisotropy, that's just something to do with the time dimension. It just makes the time dimension more or less equal to the spatial dimensions. We can play with that. That's just something I need to put in there to make it work. It has nothing to do with CG. Don't worry about it. Tolerance you've seen before, 10 to the power minus 12. So I want the same level as accuracy. Then we have this thing called prec sloppy or prec low, or the low precision. And we can configure that. CUDA has been written so well that even without recompiling, at runtime, you can run in double precision and have your sloppy precision in double, single, or indeed half, or indeed a quarter, but we haven't quite worked out how to do a quarter yet, so I've left that one out. Reliable delta, that's that delta stuff that we had next to the B. So this is basically saying that when your residual norm stops moving by this amount, trigger a restart. Good old CG, that's my inverter type, 10,000 iterations. And this load gauge, that's just the information in the gauge field. That loads in the matrix. So rather than just making a matrix of random numbers, I actually have a matrix that's sitting around. This is a matrix from a QCD simulation. This is a physical problem. This went into a paper. This is very real. This is a very real problem. Okay, let's play with it, because playing with things is fun. So we're going to have double precision target and double precision in the low stuff. So all I'm going to do now is just run conjugate gradient without any mixed precision and see what we get. Let's see what we get. Happy days. Okay. What are the important numbers? Well, the things that I care about are this. 948 was the number of iterations. How long did it take? Took 2.3 seconds. Okay, good. I can live with that, 2.3 seconds. You think? That's pretty fast. I like that. But we can do better. We know we can do better than that, right? Now remember these numbers: 948 iterations, 2.3 seconds. And if you're really, really good, you can remember a bit of this: 6.7 times 10 to the 6. That's the solution. That means that the x vector has a norm of that. So if I use mixed precision, it better get the same norm. I don't want a different answer. I absolutely do not want a different answer. So this number had better be the same. So kind of remember that, 6.79524. Remember that. I want that number to be the same. But also we have 948 iterations, 2.34 seconds. Let's play. Play. Let's see, 16. Let's now have single precision as our sloppy stuff. So now we're going to be doing double precision target, but most of the grinding and the matrix vector operations in CG, they're going to be done in single. See what happens. Okay, 948 iterations, so not much changed. 6.79524, solution hasn't changed. Oh, look at that. We were a whole second faster. That's a lot. That's nearly 50%. Just by switching to single precision. So if your solvers, or Krylov solvers, are not using mixed precision, you see immediately you're not utilizing everything that's going on in your GPU. Your GPUs do this, by the way. GPUs are very good at doing single precision very fast and half precision very fast. That's the whole point of them. That's why GPUs are so popular, is because they can really exploit how to use the proper data type for the problem at hand. If you were to just do double precision all the time, you would be wasting flops, you'd be wasting time, you'd be using far too accurate a data representation for the job at hand. So single precision is the way to go. Or maybe it's not. Maybe we can get away with half. Let's see. Let's see what happens in half precision. So now the target precision is double precision. And now most of the matrix vector operations are done in half. This is pretty bad. You know, like the ratio of double to a half is a quarter. So now we're only using a quarter of the information. Let's see what happens. $993. Okay, good. So now you see that the iterations have got a bit more. You need a few more iterations. It used to be 948. Now it's 993. So you, oh, no, I have to do like what, 40 more iterations? Well, that's all right. That's only 5%. What about my reconstructed solution? 6.79524. Good, nothing's changed. But look at that. Another half a second. Wow. So half precision really is pretty awesome. But that's not everything. We're not completely done. You see, the problem is that this problem doesn't really fit on a GPU fully. This only saturates about half of a GPU. Somebody asked about memory before. One of these GPUs has about 16 gigabytes of memory, and this problem is only about 4 or 5 gigabytes. So we're not even using the full machine. So when we saw those timings of 2.3, 1.3, 0.8, that's not as good as what we really want, which is, you know, getting half as small again, half as big again. But luckily for us, we have a slightly larger matrix. This is 24 by 24 by 24 by 64, so it's a lot bigger. So it's going to saturate the matrix. So it's going to saturate the GPU. So a lot more of the GPU memory is going to be used. So this means that we should see these nice, neat ratios appear much better. Let's do that. So wait a minute, we need to work in double-double. So we're doing the same thing again. Working in double-double with this 24. It's a much bigger problem. And you can see it's a little bit slower. It's a bit slower because there's more data to crunch, so the solver's just a bit sluggish. Whatever, that's fine. We can wait. We have the time. We have the patience. Good. Important numbers. 1362 for the iterations. Solution now is 228. Just get a general idea of that number, because you know it's not going to change, but whatever. More importantly, 11.8 seconds to solve that. At that point, you might be thinking, it's going to take a while. I've got 10,000 matrix inversions to do, and they're taking 12 seconds of time. I don't know if I don't think I'm going to graduate in time. Is what you're going to say. I'm going to have to run that thing for 2 years. I've only got 4 years for a PhD. Do I have enough time? So of course, you switch on your single precision, and we'll measure it. And single precision is about twice as fast as double precision on a GPU. Let's put that to the test. $13.62 for the iterations, 2.28, blah, blah, blah. 6.4. That's a lot better. That is getting closer to that exact factor of 2 ratio. It's not quite there because there's all sorts of latencies and things like that going on. But the bigger the problem, the better the efficiency of single precision. Let's use half. Let's see. Let's do it. We want half again. So we want something around what? We want something around 3 seconds or so, right? Let's see what happens. Half precision, same number of iterations this time, about 3.5. So it really works. That's what I'm trying to show you. It really works. I'm not just going to give you an algorithm and some math and then just say go away and trust me, mixed precision is great. Here is an algorithm that uses it, and it really does work. And we use this for our research all the time. CUDA is a superb library written by great people who know this. They are pioneering in mixed precision. and making incredible progress in lattice gauge theory because they're improving their solvers. If you were to write a proposal and say, hey, I need 500,000 core hours on a machine to do this computation, they're going to say, no, because 500,000 core hours is a lot. If you then go away and you grind away at your Krylov solver, you say, hey, I've got my Krylov solver 4 times faster. Can I have 125,000 core hours? They go, yeah, you can have 125. We can afford that. You now have a paper. You've now done some science. You've now done some research. So improving these Krylov solvers gives you the ability to do more research with less time. That's very important. This is a very practical part of science. This is why I'm teaching you this. I'm not teaching you particle physics, which is what I am, a nuclear particle physicist. I'm teaching you the Krylov solver part because it's common to everything, common to everyone. Okay, good. So that's the CUDA demonstration. If you have questions about that, please let me know. CUDA is a very complicated library. It's not a good entry point for this kind of stuff. It looks wonderful. It's like a Ferrari or a Porsche. You're like, wow, that's great. But I really wanted to know how a car works. You'd be like, well, okay, you're not going to learn how a car works by being presented with a Ferrari. You're going to need to know the inner workings, which is why I gave you this very basic conjugate gradient solver with things like an initial guess and with the information that you need to convert that CG solver I gave you into a mixed precision solver if you are feeling very brave. If you are feeling brave. It's up to you. You don't need to do it, but it's always good to have some sort of task, some sort of follow-on from a lecture. Okay, so it's gone again. So we're gonna push on now, I think, with let's see. Let me talk about how long have we got? Like 5 minutes. Let me not even talk about this. Oh no, I'm going to talk very quickly just about basic eigen decomposition and deflation, but nothing more. Just these 2 slides. So deflation is taking advantage of the fact that we know how our Krylov solvers work. They work by suppressing and enhancing eigenmodes. So once you understand this about Krylov solvers, like it's all about these eigenmodes, you can get cute and you can realize that if you just identified some of these really, really, really tiny eigenmodes, the tiny eigenmodes are the worst because those are the ones that don't change very much and you have to work really, really hard to get rid of them. If you just decide, I'm going to actually explicitly identify some of these low eigenvectors, then you can make your problem way better. So here you have your initial problem. Here's your initial residual equals the source vector. This vector represents the field that you want. And then there it is again, this terrible matrix and my initial guess, blah, blah, blah. What you do is you identify some of the low eigenmodes and you remove them from the initial guess. Because remember, this initial guess, x0, can be represented by the eigenvectors of your problem matrix. And by identifying the eigenvalues, some of the smallest eigenvalues, you give your solver a massive head start, a great head start. Because you basically said, like, I know, see, okay, this is something you have to gain. You have to like get it straight in your head and imagine in your head. Think about the smallest eigenvalues of the matrix A, the really small ones. The really, really small ones. These are the finicky ones. These are the ones I don't like. The small ones are the ones that cause me a problem. The inverse of the really small eigenvalues, those are huge. So the tiny eigenvalues of the matrix A make up a very large portion of the inverse matrix. So if you can identify some of the really, really small ones, then you're good to go. You're pretty much all the way there. And so you can use this thing called deflation to improve the solvers. You essentially change the problem from solving with this matrix A to this, what we call conditioned matrix or reduced matrix A prime. And there you go. The condition number of the original matrix is huge. The condition number of the conditioned matrix is different. The largest eigenvalues are the same, but now you've removed the smallest and now you just have some smallish ones. And A prime is a much, much easier system to solve. So that's another thing you can do. In fact, I think if I'm really cheeky, I am really cheeky, aren't I? Yeah, I'm going to do it. I wrote this eigensolver, so and I'll use it very well. Let's very quickly. Oh wait, do we have time? No, we have no time because it's 2 minutes, so we're not going to bother. Well, I could have shown you, but we have no time. So yeah, eigen decomposition, and then there's a whole boatload of stuff about multigrid stuff, which you can read at your leisure or ask questions about when I upload these slides. But for a moment, let me just quit. Let me just stop. Otherwise, this will become information overload, and nobody likes that. So well, let's just recap. What do you got? You got a conjugate gradient solver in your possession now. You can play with. You can try and break it. You can try and experiment with it. You can do all sorts of funny things with it in a very simple C language. And you also have some practical OpenACC acceleration examples. So if you had any kind of code lying around that's using CPUs, and you really kind of want to get it to work on GPUs, but you don't know where to start, this is a good place to start. If you have any kind of like I say, CPU code, you can use these Pragma OpenACC examples. And inside that repository, where is it? There it is. Yeah, you have some texts. So there's the prec problem. Yeah, that would be how you would compile it using OpenACC. You use what's called the NVC compiler, and you use those things there. Quickly show you because I like this one actually. Where is it? That one's an NV Local, yeah, 2022. Yeah. So now I just compiled all of that code that we did with OpenACC, and OpenACC gave me boatloads of information about how it accelerated my code. You should go away and try this. You should definitely go away and do it. Get hold of an NVIDIA GPU, see what you've got going on. I'm sure Joel can scratch up some resources for you, and you can play around with this on an NVIDIA GPU. I quit again. Why did I do that? Right, this is the fourth last time. I'm not going back. We're staying on the keynote. We're staying on the keynote. 4.5 megabytes, that's quite a lot, yeah. Right, so there you go, you have your OpenACC, and you can play around with it. Like I said, yeah, it's very likely in your future research that you're going to have to deal with a matrix inverter, at which point it will be a Krylov solver. There are some Jacobi type solvers out there, but they're not as sleek as Krylov solvers. Krylov solvers are robust, they're fast, and they're highly configurable. So if you find that your Krylov solver encounters a bottleneck because you're exploring a region of the phase space that makes the condition number get bigger, which is what happens in physics, by the way. You're like, I really want to know what happens when really, really light particles interact with each other. And what happens then is the condition number blows up and your current Krylov solver cannot handle the system. As a researcher, it's up to you to decide, do I want to pursue this system? Is it worth pursuing the system? Or do I move on to a different one? If it's worth pursuing the system, you're going to have to learn how to tame your Krylov solver. And now you've seen some ways in which you can break it, and you can make it, and you can make it even better. So they have that information. And lastly, yeah, you've seen that mixed precision is brilliant. And if your application does not use mixed precision, then it should. And this might seem very obvious, like, of course, why go through the trouble of telling us about mixed precision just to say to use it? Surely everybody's using it, right? No. I got my job at Berkeley because there is an application within the computer science lab that is only able to be compiled with either double or single. So they were doing all of their Krylov stuff in double. And I gave a part of this presentation. The other part was a load of other stuff. And immediately they were like, yeah, you can have a job, right? We're gonna draw up a job and you can do this for us. So my job at the moment is to improve their Krylov solvers so it uses this mixed precision. Because this is a national lab in the United States of America, and it's a very important one with a very important program that is still not using mixed precision. So if you can bring mixed precision to your Krylov solvers, you can be very useful indeed, and you can generate a lot of science with it. There's an awful lot of science, an extra science that will come simply by making Krylov solvers go fast. So there you go. So we're done. So feedback and questions, please. Thank you very much.
All right. Thank you so much, Dean.
Yeah, you bet.
Oh, I'm sorry. I never actually properly introduced you to everyone.
Oh, that's all right. Don't worry about that. Don't worry about that. Well, you can do if you want, actually. If you want, if you feel. If
Yeah, I
you
mean,
feel
I think you introduced yourself, so.
Okay. Let me just read a couple of these questions. Okay, is memory? Yeah, memory is going to be an issue. Do you know of other algorithms or applications where mixed precision is useful or promising outside of CG? Well, any kind of matrix inverter algorithm. So you've got biconjugate gradient stabilized. Okay, that's the question. That's very good. Yeah, because of course I have a boatload of extra slides. This one is called adaptive geometric multigrid. And this is a very complicated subject and takes a long time to understand. So I'll just go through the pretty pictures. You see here that we have this thing called the finest grid. This is like the matrix, the vector fields that we're dealing with. And the vector fields are very rough and they're coarse and there's all sorts of information in there and you have to preserve it. What multigrid does is it says, hey, I can give you a really good approximation to your matrix inversions or guesses to your matrix inversions simply by smoothing the fields. And then when you smooth the fields, you can see that you can coarsen the grid. So this fine field has, I don't know, let's say 1024 data points, which is a lot. The coarse grid might only have 256. So your coarse grid representations are 4 times smaller than the actual fields that you're dealing with. And if they're 4 times smaller, then they're going to be 4 times faster on a computer. So these multi-grid methods, which are, like I say, are very complicated, most definitely use mixed precision, because you can do all of this multi-grid stuff all in double precision and it will give you a nice speed up, but you don't need double precision data to represent the information that you want. So you can use mixed precision. So you would have your outer Krylov solver. So this is like the CG or the GCR, the thing that you think that you want to do the work. That will always be done in double precision. Your multi-grid preconditioner, the thing that does all of this funny business for you of like smoothing and coarsening, all of that can be done in single precision and half precision, because you only need to use low precision representations to represent this data. And then, of course, you can always use deflations and things like that. Machine learning is another field of research in which mixed precision is absolutely prevalent. In fact, machine learning is really where mixed precision came to the fore. Like, so that's where people really realized, like, wow, you don't really need to use double or single precision to do that. Google were very, good with this. They were doing things in single, and they realized, like, we don't need all of these bits. We can use half precision. And they came up. They saw the need for half precision so badly that they invented their own half precision data type. That's how useful they saw half precision. They're like, we need to invest in a new standard, bfloat 16. So there's all sorts of places outside conjugate gradient, such as machine learning and eigensolvers, for example, Lanczos eigensolvers and Arnoldi eigensolvers. Any kind of iterative matrix vector stuff that's going on, mixed precision can be used. And mixed precision is an active field of research, because there are all sorts of very, highfalutin computer science bounds on what kind of data you can represent, what ranges of data you can represent, whether or not a particular algorithm will converge depending on these bounds. And so people, are thinking really hard about the uses of mixed precision and why it works and how it works and the mathematical reasons for its convergence. And some of these questions are not really fully answered. So it's, you can make a living out of this. If mixed precision is something that you like, you can really make a living out of it. And yeah, that's just another various, just all sorts of nice new stuff using mixed precision. Any other questions? No, we're all done. Sounds like it.
I think we're good to go, Dean.
Yeah, splendid. All right, good. Well, I hope you learned something. If not, you can always email me. I will happily clarify anything that I blurted out in the past hour and a half.
Awesome.
But, yeah, happy hacking, everyone. All right, bye-bye.
I was going to